Welcome to this coding walkthrough. In this video, we'll explore LeetCode problem number 876, middle of the linked list. This is a classic problem that helps strengthen your understanding of linked lists, which are a foundational data structure in computer science. Let's dive in and break the problem down step by step. In this problem, we're tasked with finding the middle node of a singly linked list. A linked list is a sequence of nodes where each node contains a value and a pointer to the next node in the list. The goal is to identify the middle node and return it. If the list has an odd number of nodes, the middle node is straightforward to determine. However, if the list has an even number of nodes, there are two middle nodes, and we are required to return the second of those two. For the output, we don't just return the value of the middle node, but the entire sublist starting from that middle node to the end of the linked list. This ensures that the structure of the nodes after the middle is preserved and included in the result. To make this clearer, let's walk through some examples. In the first example, the input linked list is 1, 2, 3, 4, 5. This list contains 5 nodes, so the middle node is the third node, which holds the value 3. The output, therefore, is 3, 4, 5, as the return list starts from the middle node and continues to the end. In the second example, the input list is 1, 2, 3, 4, 5, 6. Here, the list has 6 nodes, meaning there are 2 middle nodes, 3 and 4. Since we need to return the second middle node, the result is 4, 5, 6. Finally, in the third example, the input is 1, a linked list with only one node. In this case, the middle node is simply the single node itself, so the output is 1. These examples illustrate different scenarios, including odd length lists, even length lists, and the smallest possible list. Now, let's consider some edge cases to ensure our solution is robust. First, if the linked list contains only one node, such as 1, the middle node is the single node itself, and our output should reflect that. Second, for a linked list with an even number of nodes, such as 1, 2, 3, 4, we must be careful to return the second middle node, which in this case is 3. Finally, when the linked list reaches the maximum constraint of 100 nodes, our solution must handle this efficiently. It's crucial to ensure that the algorithm remains optimized and performs well even with larger inputs to meet the problem's constraints. To solve the problem of finding the middle node in a linked list, we first considered the brute force approach. The intuition behind this method is straightforward: traverse the entire linked list to calculate its total length, which we'll denote as n. Once we know the length, we can determine the index of the middle node by dividing n by 2. Then, in a second traversal, we stop at this calculated index to retrieve the middle node. This approach involves two main steps: first, a full pass through the list to compute its length, and second, another pass to stop at the middle node. While this method is simple to understand and implement, it has a time complexity of O(n) due to the two traversals. Space-wise, it's efficient, requiring O(1) additional space since no extra data structures are used. However, the brute force approach has some notable drawbacks. Specifically, it requires 2 full traversals of the linked list, which can be inefficient, especially for very large lists. To address this inefficiency, we also considered a more optimized solution using the two-pointer technique. The intuition behind this method is clever. By using 2 pointers, one moving at a faster pace and the other at a slower pace, we can locate the middle node in a single traversal. The fast pointer moves 2 steps at a time, while the slow pointer moves 1 step. By the time the fast pointer reaches the end of the list, the slow pointer will have reached the middle. This observation eliminates the need for multiple passes and makes the process significantly faster. Additionally, this method still maintains the same O(1) space complexity. To implement the two-pointer approach, we start by initializing 2 pointers, slow and fast, both beginning at the head of the linked list. In each iteration, the slow pointer moves 1 step forward, while the fast pointer moves 2 steps forward. The process continues until the fast pointer either reaches the end of the list or encounters a null next node, depending on whether the list has an odd or even length. At this point, the slow pointer will be pointing to the middle node, which we can simply return. This approach is highly efficient, achieving a time complexity of O(n), since we only traverse the list once. Moreover, it requires no additional space beyond the 2 pointers, keeping the space complexity at O(1). The advantages of this method are clear: it's more efficient than the brute force approach, and its implementation is clean and minimal. Ultimately, we decided to use the optimized two-pointer approach because it balances efficiency and simplicity. While the brute force method is easier to grasp initially, its two-pass traversal is less optimal compared to the single-pass solution offered by the two-pointer technique. The key insight that makes the two-pointer method so effective is recognizing that the fast pointer speed ensures the slow pointer reaches exactly the middle of the list by the time the traversal is complete. This eliminates the need for additional length calculations or multiple passes. When comparing the two approaches, the brute force method is advantageous in its simplicity, but it falls short in efficiency for large linked lists. In contrast, the two-pointer method is both time-efficient and space-efficient, with only a slight increase in logical complexity due to the simultaneous movement of two pointers. In conclusion, the two-pointer approach offers an elegant and efficient solution to the problem of finding the middle node in a linked list. By leveraging the relative speeds of the two pointers, we can solve the problem in a single traversal with constant space, making it the optimal choice. This method strikes the perfect balance between performance and clarity, addressing the inefficiencies of the brute force approach without introducing unnecessary complexity. For these reasons, it stands out as the preferred strategy for this problem. To solve the problem of finding the middle node of a singly linked list, we use an efficient approach called the two-pointer technique. The intuition behind this method is to leverage two pointers, slow and fast, to traverse the linked list at different speeds. The slow pointer moves one step at a time, while the fast pointer moves two steps at a time. By the time the fast pointer reaches the end of the linked list, the slow pointer will be exactly at the middle. This eliminates the need for calculating the length of the list or making multiple passes, saving both time and space. Here's how the algorithm works step by step. First, we initialize both pointers, slow and fast, at the head of the linked list. Then, we start traversing the list. As long as the fast pointer and its next node are not null, we move the slow pointer one step forward and the fast pointer two steps forward. This ensures that the fast pointer progresses twice as fast as the slow pointer. Now, the termination condition for this traversal is when the fast pointer becomes null or its next node is null. This indicates that the fast pointer has reached the end of the linked list. At this point, the slow pointer will be pointing to the middle node of the list. We then return the node that the slow pointer is referencing as the result. There are several key insights to consider with this approach. The reason the two-pointer technique works is because the fast pointer moves at twice the speed of the slow pointer. As a result, when the fast pointer is at the end, the slow pointer has covered exactly half of the list, landing at the middle. This technique is efficient, requiring only a single traversal of the list, which gives it a time complexity of O(n). Additionally, it uses only two pointers, so the space complexity is constant, or O(1). When handling edge cases, this method works seamlessly. For instance, if the list contains only one node, the slow pointer will directly point to that node. If the list has an even number of nodes, the slow pointer will point to the second middle node, as specified in the problem statement. The problem involves using a singly linked list, which is a data structure where each node consists of a value and a reference to the next node in the sequence. To solve the problem efficiently, we use two pointers, slow and fast, to traverse the list. The code implementation of this approach is straightforward. First, we define the structure of a singly linked list node using the listNode class. Each node has two attributes, val, which holds the value of the node, and next, which points to the next node in the list. In the middle node function, we initialize both slow and fast pointers to the head of the list. Using a loop, we move the slow pointer one step at a time and the fast pointer two steps at a time, ensuring that the traversal stops when the fast pointer or its next node becomes null. Finally, the node referenced by the slow pointer is returned, which gives us the middle node of the list. This concise implementation captures the efficiency and simplicity of the two-pointer technique, solving the problem in O(n) time with O(1) space. This implementation solves the problem of finding the middle node of a singly linked list using the two-pointer technique. The algorithm is efficient, operating in O(n) time complexity where n is the number of nodes in the list, and O(1) space complexity since no additional data structures are used. The function starts by initializing two pointers, slow and fast, both pointing to the head of the linked list. These pointers will traverse the list at different speeds. The slow pointer moves one step at a time, while the fast pointer moves 2 steps at a time. The while loop runs as long as fast and fast.next are not null. This ensures that the traversal stops when the fast pointer reaches the end of the list. Within each iteration of the loop, slow is moved 1 step forward, and fast is moved 2 steps forward. The key insight here is that by the time the fast pointer reaches the end of the list, the slow pointer will be at the middle. This is because the fast pointer moves twice as fast as the slow pointer, effectively traversing the list in half the time. Finally, the function returns the slow pointer, which now points to the middle node of the linked list. If the list has an even number of nodes, the problem specifies returning the second middle node, which this implementation handles naturally due to the fast pointer stopping condition. This approach is optimal and widely used for problems involving linked lists, as it avoids the need for extra space or multiple passes through the list. This is the Java implementation of the middle of the linked list problem. The logic mirrors the Python solution, where we use 2 pointers, slow and fast, to efficiently find the middle node of the linked list. The slow pointer moves 1 step at a time, while the fast pointer moves 2 steps at a time. When the fast pointer reaches the end of the list, the slow pointer will be at the middle. Key differences include type declarations, the list node class definition for linked list nodes, and Java syntax for handling null checks and pointers. In this problem, the task is to find the middle node of a singly linked list. If the list has an even number of nodes, we return the second middle node. To solve this, we use a 2-pointer approach. We have a slow pointer that moves 1 step at a time and a fast pointer that moves 2 steps at a time. This ensures that when the fast pointer reaches the end of the list, the slow pointer will be at the middle node. Let's take an example with an odd number of nodes, 1-2-3-4-5. Initially, both pointers are at the head of the list, which is the node with value 1. During the first iteration, the slow pointer advances 1 step to node 2, while the fast pointer jumps 2 steps to node 3. In the second iteration, the slow pointer moves to node 3, and the fast pointer moves 2 steps further to node 5. On the third iteration, the slow pointer moves to node 4, but the fast pointer tries to move 2 steps forward and becomes null, which ends the loop. At the end of this process, the slow pointer is pointing to the node with value 3, which is the middle node for this odd length list. The output in this case is the node with value 3. Now, let's consider an example with an even number of nodes, 1-2-3-4-5-6. Again, we initialize both the slow and fast pointers at the head, which is node 1. In the first iteration, the slow pointer advances to node 2, and the fast pointer jumps to node 3. In the second iteration, the slow pointer moves to node 3, while the fast pointer advances 2 steps to node 5. In the third iteration, the slow pointer moves to node 4, and the fast pointer tries to move 2 steps forward but becomes null, causing the loop to terminate. After the loop exits for this even length list, the slow pointer is pointing to the node with value 4, which is the second middle node. The output for this example is the node with value 4. Finally, let's look at a special case where the list contains only a single node, 1. Both the slow and fast pointers start at the head of the list, which is node 1. Since the fast pointer is not null but its next pointer is null, the loop exits immediately without any iterations. Here, the slow pointer stays at the head, which is the node with value 1. The output for this case is simply the node with value 1. This 2-pointer approach works efficiently because the fast pointer moves 2 steps for every 1 step of the slow pointer. The loop terminates when the fast pointer reaches the end of the list or becomes null, and at that point, the slow pointer is guaranteed to be at the middle of the list. This method handles all edge cases, whether the list has an odd number of nodes, an even number of nodes, or just a single node. The time complexity of this solution is O(n), as we traverse the list only once, and the space complexity is O(1), as no additional data structures are used. This makes the 2-pointer technique both simple and optimal for this problem. The time complexity of our solution is O(n), where n represents the number of nodes in the linked list. To understand this, let's break it down mathematically. The while loop is the core of the algorithm, and it progresses the fast pointer by 2 steps and the slow pointer by 1 step during each iteration. The condition for the loop, while fast and fast.next, ensures that the traversal stops as soon as the fast pointer reaches or exceeds the end of the list. Since the fast pointer moves 2 nodes per iteration, the total number of iterations is roughly half the number of nodes in the list, or n/2. Because n/2 is directly proportional to n, the overall time complexity simplifies to O(n). This means the algorithm scales linearly with the size of the linked list. Now, let's discuss the space complexity, which is O(1). The algorithm achieves this by using only 2 pointers, slow and fast, both of which are initialized to the head of the linked list. There are no additional data structures, such as arrays or hash maps, involved in the solution. Since the amount of memory used does not depend on the size of the input, the space complexity remains constant. Furthermore, whether we consider the best, average, or worst case, the algorithm always processes half the list, as the fast pointer moves 2 steps at a time. This consistent behavior ensures that the time complexity remains O(n) in all scenarios, regardless of the input configuration. To further understand the efficiency of the two-pointer approach, let's compare it to a brute force solution. A naive method would involve 2 separate traversals of the list, first, to calculate the total length n, and second, to find the middle node at index n/2. While the time complexity of this approach is still O(n), since it involves O(n) for the first pass and O(n/2) for the second, it requires 2 separate traversals. The two-pointer method, in contrast, achieves the same result with just a single traversal, making it more efficient in practice. Importantly, both approaches maintain a space complexity of O(1), as neither involves additional memory usage beyond a few pointers. However, the single traversal of the two-pointer approach gives it a clear advantage in terms of runtime efficiency. Let's solidify our understanding of the current solution's time complexity with a mathematical proof. The number of iterations in the while loop is dictated by the fast pointer, which moves 2 nodes per iteration. For a linked list of size n, the fast pointer will make approximately n/2 moves before reaching the end of the list, or none. Each iteration of the loop involves constant time operations, such as pointer updates, so the total time complexity is directly proportional to n. Additionally, the space complexity remains constant at O(1), because the algorithm only uses 2 pointers, regardless of the input size. This combination of O(n), time complexity, and O(1), space complexity makes the solution optimal for finding the middle of a linked list. When solving this problem, there are several common mistakes you'll want to avoid. First, some people misinterpret the problem statement and think they need to return the index of the middle node instead of the node itself. Remember, the goal is to return the actual node. Another issue arises with even length lists. In these cases, the problem specifies returning the second middle node, but it's easy to mistakenly stop at the first one instead. Additionally, some solutions use extra space unnecessarily, such as storing all the nodes in an array. While this may work, it violates the space constraint of O(1), which is key for optimal solutions. Off-by-one errors are another common pitfall, particularly in the two-pass approach where calculating the middle index incorrectly can lead to results being slightly off. Finally, it's crucial to handle edge cases effectively. For instance, a list with just one node or a very large list up to 10,000 nodes can expose weaknesses in your solution. Testing these scenarios is essential to ensure robustness. Now, let's discuss how this problem ties into interview scenarios. One of the key insights here is that this problem is a classic example of the two-pointer technique. Mastering this approach is vital for efficiently traversing linked lists, a skill that interviewers love to test. In fact, this technique also lays the foundation for tackling other linked list problems, such as detecting cycles or finding specific nodes. The two-pointer approach is optimal, offering O(n) time and O(1) space complexity, and it's important to articulate why it works so well. For instance, the fast pointer moves twice as quickly as the slow pointer, ensuring the slow pointer lands on the middle node when the fast pointer reaches the end. You might also encounter follow-up questions during interviews, like finding the kth node from the end or dealing with doubly linked lists. These variations test your ability to adapt your knowledge to slightly different scenarios, so it's good to practice explaining how your approach can be modified. This problem also connects to several related problems that are worth exploring. For example, LeetCode number 141 asks you to detect cycles in a linked list, another application of the two-pointer technique. Similarly, in LeetCode number 160, you're tasked with finding the intersection node of 2 linked lists, a challenge that often builds on some of the same traversal concepts. LeetCode number 234 focuses on determining whether a linked list is a palindrome, which requires reversing or manipulating pointers effectively. Lastly, LeetCode number 19 involves removing the nth node from the end of a list, which is another classic problem where the two-pointer approach shines. By practicing these related problems, you'll not only deepen your understanding of linked lists but also develop a strong intuition for recognizing patterns and applying efficient techniques in different contexts. Finally, let's take a look at some alternative approaches and their trade-offs. One common method is the two-pass approach, where you first traverse the list to calculate its length and then make a second pass to find the middle node. This approach is straightforward, but because it requires two separate traversals, it's less efficient than the two-pointer technique. Another option is the array-based approach, where you store all the nodes in an array and then simply access the middle node using its index. While easy to implement, this method uses O(n) space, which violates the problem's O(1) space constraint. A less common solution involves recursion, where you traverse the list recursively and track indices to find the middle node. However, this approach is inefficient due to the O(n) space required for the recursion stack and is rarely practical. Understanding these alternatives helps you appreciate why the two-pointer technique is the best choice for this problem. Great job! To summarize, we tackled the middle of the linked list problem by exploring efficient algorithms and key concepts like the two-pointer technique. Remember, linked lists are common in interviews, so keep practicing. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!